I'll be talking about real-time sound propagation, which is based on wave simulation. So, perceptually convincing sound propagation is essential for virtual environments. And what makes this problem tough is the physical complexity of how sound waves propagate in a scene. Sound waves are effectively pressure waves propagating in air. And as you can see in this cathedral scene, if a pulse of sound is emitted at a certain location, over a short period of 100 milliseconds, it becomes quite complicated. And many of these wave effects are perceivable to us. The state of the art in current interactive applications like games is to use hand-tuned filters for assigning this. And this becomes difficult and tedious. So artists use a rough classification of events that might happen in real time, like occlusion, obstructions, and exclusion. And to handle all these things in a fashion which takes care of all possibilities at real time is difficult. What simulated propagation can do is do all this automatically and give detailed, realistic acoustics, which depends on the scene and where the source and listener are in the scene. There has been a lot of interesting previous work in this area. There has been work on beam tracing, frustum tracing, and the image source method. And all of these methods are geometric in nature in that they treat sound like it propagates like light rays. And this works well for high frequencies, but for lower frequencies, diffraction, handling diffraction and scattering, and other wave effects becomes quite challenging. Our approach, in contrast, is based on wave simulation, and it can capture effects like diffraction, which leads to smooth attenuation of sound volume as you walk behind obstructions, and low-pass filtering that happens in these cases. It can handle scattering from complex-shaped surfaces, as well as dense reverberation. And this approach, because wave simulation is hard to do in real time, and it's not possible right now in current machines, we use a pre-compute and render approach. So this is similar in philosophy to the work by James et al. In 2006, but they're attacking the problem of sound radiation from objects. And our approach solves the problem of how such radiated sound would propagate in the scene. So these are complementary problems. So I'd begin by giving you a short demo of a demonstration of the sound engine we have developed based on our technology and compare it with the game Half-Life 2's default sound engine.
And started at the shadows that leapt upon the cavern's walls, but inseparable from instinct is its dark twin, superstition. Instinct is inextricably bound to unreasoning impulse, and today they face and started at the shadows that leapt upon the cavern's walls, but inseparable from instinct is its dark twin, superstition. Instinct is inextricably bound to unreasoning impulses, and today they clearly see its true nature.
So as you can observe, there's much more reverberation which corresponds to the scene, and also when you walk behind the wall, there's realistic obstruction.
For giving us respite from this howling fire. They have force.
So in this case, you're standing in a small region of the scene and you get the realistic reverberation according to it with our engine. So to give you an idea of how sound propagation is done through a pre-compute and render approach, I'll take a simple example of a source and listener standing above a flat ground. In this case, suppose you clap at some position giving out an impulsive sound. It travels through two paths, one the direct path and the other one is reflected from the ground. And if you record the response of the listener, you'll get two peaks corresponding to this, because the direct path takes some delay to get to the listener from the source, and also there's some distance attenuation. And for the reflected path, the path length is longer, so the delay is longer, and also there's some absorption from the ground. So depending on how the sound interacts with the scene, you get lots of different peaks in reality. So this quantity is called the impulse response, of how the pressure changes with respect to time at the listener if an impulse is emitted at the source, and it's the most important acoustical quantity. This is what we want to pre-compute throughout the scene, and which can be used in runtime to auralize the sound. So at runtime, the source is emitting some arbitrary signal, and what we want to estimate is what the listener would hear in this case. So the basic intuition is sound would propagate in the same way no matter what the signal is, and what you can do is look at the impulse response and apply delay and amplification to the sound depending on these peaks and compute the final sound. This is exactly equivalent to the mathematical operation of convolution. So effectively, you pre-compute all the impulse responses, and then at runtime, whatever the signal of the source is, you convolve the two, and you get the final sound to play at the listener. Now this is assuming a static source and listener. What if the listener moves, or the source moves? In that case, the impulse response changes, because there's longer delay to get from the source to listener, there's different attenuation characteristics and complex interactions with the scene. This means that impulse responses vary spatially, and the sampling space we have is seven-dimensional, because the source can move in 3D, the listener can move in 3D, and for each source-listener pair in space, we have an impulse response, which is a function of time. This can be reduced to 6 dimensions by restricting the listener to a 2.5D surface. So in most games, the listener is moving around on a 2D plane or walking at different floors in a building, so that can be used. But even after the 6-dimensional reduction, the brute force sampling is still infeasible. To give you a quick intuition, let's consider this scene, the Citadel scene, which I'll be demoing later. If we do brute force sampling on this scene, on the grid on which the simulation is performed, it would take 200 gigabytes to store all the results. This is clearly infeasible. Even if we subsample the spatial grid at about a 1 meter resolution, it still takes 60 gigabytes. And it introduces another problem, which is how to interpolate the impulse responses recorded on this coarse grid. Our main contribution is a compact representation for impulse responses that leads to 100 times reduction in the memory usage for each of these impulse responses that are being stored. And it works with the band-limited results of wave simulation along with perceptually plausible extrapolation. Our technique works on a coarse grid about 1 meter resolution, and we do perceptually plausible interpolation of the impulse responses to avoid all the artifacts from sampling on a coarse grid. The end effect is we can do real-time wave-based acoustics, which has automatic correspondence to scene geometry. So here's a basic overview of our approach. So we have a coarse grid in space about 1 to 2 meters, and the samples I'm showing are the listener samples on which the impulse responses are recorded. So we place a source at some position, do a wave simulation from there. We send a pulse and do a complete wave simulation, and the response is recorded at all listener locations. And the same is repeated from all source locations. And what I'm showing here are 2D grids. These are just for illustrative purposes. Actually, one of these is on a 3D grid and the other on a 2D grid, and we use acoustic reciprocity, but I'm not going to go into the details of that. Please refer to the paper for that. So once these simulations are run, we take the impulse responses and compress them. And that's the main thing we're doing. To give you a concrete idea of how these wave simulations are done, I'm going to take the example of this small scene taken here. The simulator we are using for wave simulation is ARD, which was our prior work in 2009. And this simulator is pretty fast and memory efficient. But with wave simulators, the cost increases prohibitively with frequency. So because of time and memory constraints during pre-computation, these simulations are usually band limited to about 1 kilohertz. But if more computation is available, more detailed simulations could be done to higher frequencies without affecting the runtime memory usage and performance. So this is how the simulations typically look like. So you place this you take one of the potential source samples, you run a simulation from there of a Gaussian pulse, which is band limited, and you record how the field evolves over time. And notice that only one simulation gives you the response at a lot of listener locations. And what we do is take the response that's recorded for these. So here's an example response, which looks quite complicated. And what we do is to encode this compactly while preserving its perceptually salient aspects. And we do this by exploiting well-known facts in room acoustics and psychoacoustics of how we perceive sounds in acoustic spaces. So I'll take the simple example of this scene shown with the source and listener. The first sound that gets from the source to listener is the direct path. And it gives us a sense of direction in a space where the source is. And the direct sound could be diffracted at an obstacle, such as in this case. This is followed by strong reflections from specular reflectors and other loud contributions, which come in early after the direct sound, and I call the early reflections, and give us a sense of loudness and timbre of the sound. And the early reflections perceptually change significantly at different points in the scene, and usually is about 50 to 100 milliseconds. This is followed by many small contributions which are very close together in time, and this is called the late reverberation phase, which is the sense of echo in a scene like you're hearing in the hall right now. And this is characterized mainly by the decay envelope in time and doesn't show a significant variation in a space. Like in this room, the echo pretty much stays the same everywhere, so the late reverberation corresponds to that. So to give you an intuition of this, I'm going to play a clip with our sound engine and play it with only the direct sound, then with the early reflections, and then with late reverberations added in. So you should keep in mind that this room is adding reverberation of its own on top of these. So if you really want to hear these demos, you should see the video. I'll have a link at the end. So now I'm going to describe how we compress these impulse responses that are recorded at different locations. So suppose you place the source somewhere on a wave simulation and it gives you the response at all listener locations. Let's consider one of those listener locations as shown. And I'm showing a schematic of what the response is recorded at the listener at the top of the diagram. The first thing we do is to perform a peak detection on this. And the way it's done is to just look for local extrema in the response. And then we extract the delays and amplitudes of these peaks and store them. The main idea of doing this is these peak delays and amplitudes correspond to the different wavefronts arriving at the listener after getting reflected or diffracted in the scene, and capture the time domain information as well as interference effects in the recorded response. But these don't capture all the information, and I'll get to that later, how we extract the remaining information. For the first simulation in a room, we extract the late reverberation and separate it out. And the way we do it is to look at the echo density in the impulse response, and once it crosses a threshold, we segment out the remaining impulse response as the late reverberation. And this is only recorded once per room. So this leads to a 10 times reduction in memory and pre-computation time, because the early reflection phase is about 1/10 the length in time. And all the future simulations are limited to only the length of the early reflection phase. So this leads to a reduction in the pre-computation time as well, along with the memory. So in the rest of this discussion, I'll be focusing only on the early reflection part, because the late reverberation is just stored once per room. So as I said, the peaks don't capture all the information in the recorded response. So to find out what this residual information is, we look at the frequency domain instead of the time domain. So we consider the frequency response, the analog of the impulse response in frequency domain, as shown on the right here, that the simulator generated. And this is band limited. So above a certain frequency, there's no information. And we look at what the peaks got extracted out of this information. So this captures oscillations in the frequency trend intuitively, but they don't capture the overall downward trend that might be present when there's diffraction. So if there's a wall between you and the source and the sound has to turn around it, there's a low-pass filtering effect that's going on. And we need to capture that too. So to extract that residual frequency trend, we divide these two, and that gives us a frequency trend. That is then extrapolated to higher frequencies, as shown on the bottom right here. And this extrapolation is, of course, approximate, and the only way to get this information exactly is to do a wave simulation to a higher frequency, and that can be done if a lot of pre-computation is available. And what we store finally is these peak times and amplitudes, plus this frequency trend sampled in octave bands. And this information gives a 10 times reduction in memory usage compared to just storing the output of the simulated response. So this is the information that's stored at pre-computation time, this compressed impulse responses. And at runtime, the first thing we need to do is do spatial interpolation, because the samples are on a 1 or 2 meter grid, and we need to interpolate and find the corresponding impulse response. It turns out that you could do standard bilinear interpolation, but that leads to problems. So we compute the interpolation weights using bilinear or trilinear interpolation, but we use them differently. Let me describe how. So let's go back to the simple case of just a ground plane, and you record the impulse response at one location. It looks like what's shown on the top left. And if the listener moves, you get another impulse response. Now, if you just took linear interpolation weights and did linear interpolation on this, at this point shown in the middle, what you'd get is something like what's shown on the right, and there's peak aliasing. And what happens perceptually because of this is as the listener moves between these points, the loudness fluctuates and oscillates. And that leads to bad perceptual effects. What we do instead is set up a peak correspondence between the red and blue peaks. I won't go into the details of how we do the correspondence, that's in the paper. But once we have done that, we interpolate the times and amplitudes of the peaks instead. So we consider the red peaks and get this, consider the blue peaks and get this. This corresponds more closely to what's happening in reality and doesn't lead to as much perceptual artifacts. So in this case, there's no aliasing. And once this impulse response is computed, all we need to do is take it and convolve it with the input sound. And that's done in the frequency domain because time domain convolution is very expensive for the dense filters we have. So we do an FFT and do this convolution, and we perform the FFT using Intel MKL. So now I'm going to go through the results of our work. So this first demo is on the Citadel game environment from Half-Life 2. And what we're showing here is if you walk from a small room or a large room, there's a lot of change in reverberation. And also that we can handle complex geometry in the scene.
Hello, welcome to an audio tour of our system. We pre-compute wave propagation in arbitrary static 3D scenes like this one and oralize in real time. Our system handles moving sources. Note the scanners as they pass by. We now progress through a narrow corridor. Note the change in reverberation. Our system handles complex geometry like the fans in this small room.
Okay, so the next demo is on a walkway scene. This is a simple scene that demonstrates the smooth attenuation and sound volume as you walk behind walls. The source is the gramophone. So as you see, as you walk out behind the wall, the volume again increases smoothly and as you'd expect in reality. This next demo shows sound focusing beneath the concave reflector that's in this scene, and you might notice that the loudness increases beneath the...
1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8.
So as you can see, as you walk out of it, the volume decreases again. And this next demo compares the acoustics in an empty versus a furnished living room, which we notice a lot in reality. And the scattering from the furniture in a full room changes the acoustics a lot. Next, I'm going to demo the integration of our sound engine with Half-Life 2.
Overpowering force.
Okay, so the cost of the system takes about 5% of a core for handling a single sound source, and the memory is in a few hundred megabytes. The pre-computation is a few hours per scene. In conclusion, I presented the first real-time wave-based propagation engine that can handle all wave effects and handle moving sources and listener. We presented a compact IR encoding scheme that takes 100 times less memory, and along with fast, high-quality IR interpolation, we can handle moving sources and listener. There's a lot of future work in this area. We could reduce the memory usage further by using better IR compression, lower-level improvements like going to an 8-bit decibel scale. And to increase the scalability, we could use the cells and portals approximation for sound, and limited dynamic geometry could be handled by using precomputed frequency-dependent occlusion factors. Also, the convolutions could be done on the GPU to make them much faster. Thank you.
So we're running a little bit late. If we can take one question. Doug.
Hi, this is Doug James from Cornell. I really like this work, and I think the wave effects make a huge difference. I had just one question about, at this point, it's a sort of a scalar wave equation where you have a source and listener location. And I was wondering how you would include directionality effects, both for the directionality of the listener for head-related transfer function effects, as well as directionality of sources, which we can represent using acoustic transfer functions and whatnot.
Yeah, so that adds one more dimension to our sampling effectively. And the difficult thing there would be how to parameterize this properly. We could simply sample the source from different directions or the listener from different directions, but that's going to be difficult. So what we need to find out is one good parameterization for source directivity would be to use a combination of multiple and dipole sources, as you did in your work. So we could use something like that, and at runtime we could sample the dipole directions, like 3 different directions and different dipole positionings, but the relative position of the dipoles would stay the same because it's the same object. So you could handle a lot of dipole and monopole sources, and that seems to be a good parameterization for source sounds. For listeners, there's only one listener, so we could do a much finer sampling.
I was wondering if you took into account the material properties of the objects in the scene when you did the sound reflections, like soft objects versus...
Yes, we do. So the wave simulation handles all the material properties and the reflectivities of different materials, etc.
Okay, well, let's thank the speaker again. So